Okay, so this is the 2014 Semester 1 Revision Seminar for Maths 1B, and I've had quite a list of requests, but we're going to start with quadrics and see how far we get, and anything else I do will be in another seminar. This is just for the benefit of people listening on the video. Okay. So, as far as I can tell, the reason that conics and quadrics are in this course is so that you have a purpose for doing orthogonal diagonalization. That's as far as I can tell. Other than the fact that, just logically, mathematically, you spend a lot of time in Maths 1A and in Maths 1B as well talking about planes and lines and that sort of thing, and those sorts of objects are defined by linear equations. So, a linear equation will give you a plane or a line, depending on whether you're in R2 or R3 and how many equations you've got. And the next step up from that is quadratic equations. And the objects that quadratic equations make are called conics and quadrics. Technically conic sections, because they were invented, conic sections were invented originally because you actually sliced a cone into pieces, but there are some conic sections you can't make that way, and so we just call them conics now. Okay, and so it seems like a natural progression to move to quadratic equations next. And some of the quadrics are actually two variable functions, so that matches nicely with, well, it matches, possibly not nicely, but it matches with the two variable calculus you do in Maths 1B. And you learn, if you're doing some flavours of engineering, you'll do engineering Maths 2B, and you'll continue doing multivariable calculus then. And it'll a lot be based on lines and planes and conics and that sort of thing. Personally, I think quadrics are cool because I did my PhD on quadrics, so that's my favourite bit. So I love quadrics, they're really awesome, and it makes me sad that there's so little talk about them, like 2 pages about quadrics, because they're really cool. So I will tell you what I know about them that's useful for you. I won't go into everything. So your general quadratic equation means that you could have x squareds, you could have y squareds, and you could have xy's, and if you're in 3D you could also have zx's and zy's and z squareds. And you can also have all the linear terms as well and a constant, so you get this big quadratic equation that might look like this. So that's an example of a quadratic equation that we're talking about. And those a's and b's aren't unknowns, aren't variables, they're unknowns. So usually you know what they are, okay? And the idea is that any equation of any kind, quadratic or linear or otherwise, defines an object, and that object, you find it by figuring out the points that satisfy the equation. So fundamentally, all sets of all objects with equations, the purpose of the equation is to tell you whether a point is on the object or not. Okay? So if I wanted to know, so I'm going to write that down. Okay, so the purpose of an equation is to tell if a point is on the object or not. That's fundamentally what an equation of any kind is for. So for example, is the point, 1, 3 on the conic x squared plus 3xy minus y squared plus x plus 3 equals 0. Okay, if I ask that question, what I would do is I would sub the coordinates into here and see if it works. So 1 squared plus 3 times 1 times 3 minus 3 squared plus 1 plus 3 is 1 plus 9 minus 9 plus 1 plus 3. So that's giving me 5, which is not 0. So no, it's not, because it doesn't satisfy the equation. But if it did come out to 0, then it would be on that conic, whatever that conic is. It's probably a hyperbola because of the minus. Can't tell yet. So fundamentally, that's what an equation is for. And you'll find every so often they will ask you something that will require you to use the fact that the point being on the conic means that if you sub it into the equation, it will work. One of the Maple TA questions required you to do that. It would say, ax squared plus by squared plus cz squared equals 1 is a hyperboloid of 2 sheets that passes through this point. Give me some possible values of a, b, c. And you had to know that if you sub it in, then it would work. Okay, so that's the fundamental purpose of any equation, linear or quadratic or otherwise. I can't stress that enough. Okay, but the big idea in maths is that even though that's the fundamental purpose of an equation, if we had to sub in every point in, a zillion points in to figure out where the object was, it would be a waste of our time. So the fundamental idea of algebra and how it relates to geometry is that if I do that, certain aspects of that equation should correspond to certain properties of the object that it describes. Okay, so that's the main the fundamental purpose of an equation. But we can also say, but aspects of the equation, of the algebra, will tell you about the geometry. So just like way back in school, when you see y equals mx plus c, fundamentally all that is for saying, well, if I have a point, I want to know if it's on the line, I can sub it in, and if it works, it's on the line, and if it doesn't work, it's not on the line. But I also know that if I look at that equation written that way, that the c is where it crosses the y-axis and the m is the slope. So aspects of the equation tell you about the object that the equation defines. And so the whole purpose of what we do with all the orthogonal diagonalization is to rewrite our equation in a certain way so that it's easier to tell what object it describes. In the same way that with a quadratic equation, if I have it written as y equals something, if I factorize it, then it will tell me what the zeros are. But if I complete the square, it will tell me what the vertex is. So if I do certain algebraic things, it will tell me things about the object. So that's what I'm going to do with these equations. I'm going to rewrite them in a way that means that I can tell what they are. Okay? So, just like with lines, there's a standard version of the equation of a line that tells you things about the line, y equals mx plus c. Quadrics and conics have their own standard versions that tell you about if you can make your equation look that way, then you will know precisely what it looks like just from the equation, and you won't have to test a zillion points to see if they're on it or not. Okay, that's the big idea that's going on here. So, the first step is your standard ones. So the ones in standard form. Okay, so when you're looking at the standard form of a conic or a quadric, quadric is the name of the 3D version, when you're looking at the standard form of a conic or a quadric, you need to know what to focus on that distinguishes one equation from another. And the things you need to focus on are whether the coefficients, the variables are squared or not, and if they are squared, whether they have a plus or a minus on them. That's the most important information to tell you what they are. If they're all squared, then what the constant is doing will tell you something useful. But if one of them, if they're not all squared, one of them's not squared, then the constant's irrelevant. And finally, you also need to check if all of the variables are there. So if there's a missing variable, so there's no z, for example, that tells you something interesting about it as well. Okay, so there's those three questions. So are all the variables there? So how many variables are actually in the equation. How many variables are in the equation? How many of them have squares? You know. Are they all squared or not? If they're not all squared, so the ones that are squared, are they plus or minus? And if they are all squared, then what's the constant doing? Okay, they're the main questions you should ask yourself because that helps you to distinguish between them. Now in 2 dimensions it's actually much, I'm just going to add this. In 2 dimensions it's much easier because there's less options for what could happen. So, your standard conics and quadrics, so I'll do conics first. So conics are in 2D, so it'll only be an x and or a y. And so the fundamental ones have all the variables there. Okay? So both variables are there and they're both squared. And so what you'll have is you'll have something like x squared plus y squared equals 1. That would be a circle, and it would still be sort of circular if I change the coefficients of x and y, and it would be an ellipse then. Okay? So I think about it as just the x squared and the y squared, and I put the a's in later, but the actual coefficients are irrelevant. It's just the fact that they're both positive that makes it an ellipse. Okay? So technically this is your standard form. I quite like to write it like this because that gives me a real feeling that it's x squared and y squared. But your lecturer won't write it that way, so neither will I. Okay? Okay. Maybe I will. Anyway. That's an ellipse, okay? And I will talk about what the ellipse is shaped like in a minute, but I just want to talk about the general feeling first. So that's both variables squared there, and they're both squared. And that's an ellipse. The other possibility is if... well, let's think about this. Okay, so there are 4 possibilities for how those pluses and minuses could be arranged, right? So I could have both of them positive here, and as long as I arrange for that one to always be positive, I'll be good. So both of them positive, and that would be an ellipse. They could, one could be positive and the other one could be negative. So this is both positive, both negative, not both negative. One positive. So one of them is negative. So it could be the x that has the negative, as long as the other one's positive, it doesn't matter. And this is a hyperbola. And it could be, so we've got both positive, we've got only one positive, and the only other option would be if they're both negative. And I know that you haven't seen that, but it's worth putting them in. Like that. There's no solutions to that. You can't have negative number equals 1. That's impossible. And so this is empty because there's no solutions. Just thought I should point it out. And there is one more option. We do need to consider what's going on with the constant. Okay, so if they're both positive and the constant is 0, so I've got my constant is 1, if they're both positive and the constant is 0, that's a single point. It's like a circle of radius 0, basically. And if they're both, so both negative and constant 0 is the same as both positive and constant 0 because it's just times by negative 1. And we could have 1 negative and constant 0 and what that gives me is 2 lines. Okay, so there's heaps more options than you thought. The key ones, the ones that are the most important, are your ellipse and your hyperbola. But I do want to point out that these come in families. Your ellipse there, well, this one's really similar to your ellipse because it's an ellipse with 0 radius in both directions. And so these three are sort of in the same family. They're in the ellipse family. And so is this one. This one's in the ellipse family too. Because I could actually see it as x squared plus y squared equals minus 1. That's another way of seeing it. Okay, so those three are in the ellipse family. What you imagine is that by changing your a's and b's, you can change your radius. If you make it small enough, it becomes a point. And if you make it too small, it disappears entirely. And these other two are in the same family as each other as well. So you've got the hyperbola. And in the hyperbola family, there is also the 2 lines. And so you can imagine your hyperbola getting closer, narrower and narrower in the middle until the 2 branches meet and it becomes 2 lines. So there you're both variables, both squared families.
What are the 2 lines coming like? Are they coming in like that?
I will tell you that in a second. I just want to actually run through the things first. And then, so what if you have both variables and only one of them squared? So my both variables and only one is squared. Your standard version of that is actually this. Like that. But if you want to write it like the others, you can have like x squared plus y equals 0. And note that the constant is irrelevant here, so there might be a constant. It might actually be, normally that's traditionally written this way, okay? But you can, if you want to, write it like this way, like the others, if you want to. So, but this is the traditional standard version of a parabola, or you could have x equals ky squared as well, and it could be plus or minus as well, so the k could be negative. So technically the squared ones being positive or negative won't change the shape of it. It'll change which direction it points, but it'll only change the shape if everything's squared. So back here, that's actually if all squared as well. The squared ones are positive and negative. Only if they're all squared does that make a difference to what shape it is. It always makes a difference to which way up it is, but it doesn't make a difference to the shape. So this is a parabola. And since both the variables there and they're unsquared, that's actually the only option for that situation. But then the other situation is that if you have both variables there and they're neither squared, it's not a quadric, it's a line, so we can skip that one. If you only have one of the variables there, to be a conic, it has to be squared, and so you've only got one variable. And if you've got one variable, it has to be squared. And so you've got these 3 options. You either get x squared equals a positive number, so it'll be like k, in which case you'll get 2 lines, parallel lines. So, because it'll be x equals plus k and x equals minus k. So this is positive. Or you'll get x squared is 0, in which case you'll get that's just the y-axis because it's x equals 0, so you'll get one line. Or if you're really unlucky, you'll get x squared is like minus k, where k is positive, in which case there's no solutions. So it's empty. So they are all the options for things that could happen. And of course, if there's no squares, then there's straight lines. So we don't have to worry about them. So in this family, these are all part of the same family. Okay, your parabola and your other ones, they're all part of the same family as each other, because that k can be considered to be the coefficient of y. So, yeah. So parabolas are in the all the parallel ones made of lines, of parallel lines are in the parabola family. Okay, so I was asked what do they look like. Well, I'll just do a quick tiny sketch of each of them, because I don't remember this in terms of names, I just have a picture in my head. My ellipse will look like that. Empty, there's nothing there at all. Nothing. A single point like that. So they're the ones in the ellipse family. Your hyperbola will have two branches, like that, and they'll go on forever. And there's technically some asymptotes that it gets closer and closer to, like that. So when you have the two lines, it's just the two asymptotes. That's what the two lines are. So these two lines are the asymptotes that you would have gotten if there was a 1 in that spot. They used to expect you to sketch conics in exams, and I'm not sure if that's true anymore. Yeah?
Is that a useful way of finding out what it looks like? You said it equals 0 rather than constant.
You can, yes. I will actually show you a way of knowing what it looks like. But yes, so for those listening, is it a useful way to know what your hyperbola looks like, to set it equal to 0 and find out what those lines are? Yes, that works quite well, actually. I have a different method. Your parabola will look like that. It may go sideways depending on which way around it is. Your two parallel lines will have the tendency to be looked like that, a single line like that, and this is empty again, there's nothing there at all, which I draw by a little vanishing symbol, right? Something has disappeared. So you can imagine these two as your two lines get closer and closer together until they get there, and then because if they get the distance between them gets negative and they disappear. So, okay, that's what conics look like. Okay, and before I move on to quadrics, I do want to show you my method of drawing conics, because I figured it out myself and I'm extremely proud of it. So I like it. So drawing conics in standard form, I use a box to draw my conic. Okay, so all my conics live in boxes, and the size of the box is determined by the A and the B. So this is just for parabolas and hyperbolas and ellipses, but it does work for all of them actually, if you do it in the right way. So the idea is that you'll have something like this. I'll do my ellipse first. Okay. Now, if those A and B were both 1, it would be a circle, right? Of radius 1. Without those, it's a circle of radius 1. And that circle would fit neatly in this little square. And so what I'm actually going to do is I'm going to do the same thing. So I know that if I take any equation and I divide the x by something at the place where it is, then that will stretch it out by A. If I divide the x by A, that stretches it out by A. So what I'm going to imagine is that I have my x and y axes, and I go A and minus A in the x-axis, and b and minus b in the y-axis, and I'm going to draw a box. Not that I need the box, but it does help to match with the other things. And my ellipse lives inside that box. Okay, it goes to the edges of the box. Now we're all hopefully fairly familiar with how to do ellipses that way, but the reason I draw the box is so that it matches more easily with my hyperbola, which also lives in a box. Okay. This hyperbola has a minus here, and it lives in a box too. So I use the A and the B to draw the same box. Okay. Now I know that my hyperbola has asymptotes. They pass through the corners of the box. That's where the asymptotes are. So if it was just x squared on a minus x squared on y, a squared minus y squared on b squared equals 0, that would be the two lines, the diagonals of the box. So the final thing is I need to figure out where the hyperbola is. Now in an ellipse there's only one place to live, way to live inside the box. For the hyperbola has two branches. It could be here or it could be here. And so I need to decide, and I decide that by just trying to see whether it meets one of the axes. So the y-axis would happen if x was 0, and I don't get any solutions, so this one doesn't meet the y-axis, because there's no solutions to that equation. So since it doesn't meet the y-axis, it must be over here. You also know that the hole in your hyperbola will be at the place where the negative is. And that's true in 3D as well. The hole in your object will be at the place where the negatives are. So it happens in 3D too. So just to be clear on how this worked, if I had minus x squared on a squared plus y squared on b squared equals 1, I would still draw my box. Like that. I would still have the same asymptotes. Oh, that's supposed to go through the origin, sorry. And this time, if I look at the y-axis, I do get solutions. It meets the y-axis, and so therefore it must be up here. And it heads towards its asymptotes. And notice that the hole here is matching with where the minus is. The minus is on the x, so the hole is on the x-axis. That's how I draw hyperbolas. Parabolas match with that too, just so that you know, because this is my favourite part, this one. It works best if you put the k down here, just so that you can make it match nicely. It doesn't really matter, but notice that this is y on b, and so I just like to make it have something on something. And it will work just as well if there's an a squared here too. That will work fine. So you can actually make it look like whatever you want, and that will work fine. So I'm the sort of person who will write a parabola like this. Y on b equals x squared on a squared. That's a parabola. And you can use the same b and a, just the denominators of where the x and the y are, to make your box. Minus a, minus b, and there's my box, which is supposed to be equal on both sides. And parabolas live in the middle of the box, so your parabola will have to pass through the origin, and it will go through this point, and that point, and that point. Like that. That's how I draw them, and I think it's fun. Yes. But normally, I mean, it's just y equals something x squared, and you know what that looks like. It's supposed to look like a parabola, but if you want to know exactly where it is, that's how you can do it. And if it was y equals minus x squared, it would be down here. And if it was x equals y squared, it would be over here. And if it was x equals minus y squared, it will be over here. And you'll notice that because there are 4 places the parabola could be, there are 4 options for what its equation could look like. Whereas there's only one way to put an ellipse in a box, and so there's only one possible equation for that. That's how I do it. Okay. And incidentally, if I had x squared on a squared equals 0, those would be the parallel lines there on the edges of the box. So this can be used to draw all of them. So cool. Okay, so that's drawing conics. And then the quadrics have their own things, and there's like about 20 3D quadrics, but you don't have to remember all of them. You're only expected to remember about 8 of them. And it's the same characterization process. You're saying, well, how many are all the variables there? If they are, how many of them are squared? The squared ones, are they positive or negative? What's the constant? Okay, so, and I actually have, just to show you, I'm pretty sure it's here. Oh look, there's the drawing conics handout that I did last time I did conics. Oh, I was sure it was here. Okay, I'll have to put it up. I actually have a table that has all of them in them, with how many there are and how many are squared both ways that you can have a look at, and I might just chuck that into the handout at this spot, okay? So for quadrics, I will draw pictures of the other ones. Thank you. Refer to the table that I will put in later. But there's a few main ones that you need to remember. There is this one. That's an ellipsoid. And you can remember that because it's like an ellipse, it's just 3-dimensional. So it's the same. But do note that if there's a 0 in that final spot, it will be a single point. And if there's a negative 1 in that final spot, it will be empty. Exactly the same way as the ellipse works. Okay, you can imagine the radius getting smaller and smaller and smaller until it disappears entirely. So ellipsoids have 3 members of the family as well. One of them is a point, one of them is empty.
Are you assuming that the coefficients A, B, and C are positive in this?
Yes, because they're squared. Because these are squared, they have to be positive. That's why you do them as squares. So I don't focus on the A, B's and C's, it's actually just the top I'm looking at, and I'll often just write it with x squared, y squared and z squared, and I would tend to write it as a capital to remind me that it's not the same. So one negative out of the 3, it doesn't matter which one it is, will be a hyperboloid of one sheet. In the Maths Learning Centre, there is two models made out of red string that you may have noticed. The one that's sort of circular, that's the hyperboloid of one sheet, sort of nuclear power plant shaped. And there's a good reason why they shaped nuclear power plants in that shape. Rockets are built in that shape too, but the curve is too gentle for us to notice. So, yes, there are really good reasons to build things in the shape of a hyperboloid of one sheet. Because of the way that it's quite a strong shape, and also the way that vibrations run up and down the surface means that it's unlikely for your rocket to explode while it's on the launch platform. So, yes, very cool. So, hyperboloid of one sheet, and you know which direction it points by this minus. That minus will be the hole in the hyperboloid of one sheet. So it'll be sort of this shape, right? And it goes up and down forever. And the direction of this hole here, right, that's the z-axis for this one, because that's where the minus is. If the minus was here, that would be on the y-axis instead. So, yeah, that's my z-axis there. The very narrowest part of it is on the xy plane. So, yes. I know it's a hyperboloid as well because if I cover up one of the variables, it looks like a hyperbola. So if I cover up the x, that's the equation of a hyperbola. And so if I do it, if I slice it in the yz plane, the slice will be a hyperbola. If I slice it so that there's x and z, that will be a hyperbola too. So two of the directions are hyperbolas, so it is named hyperboloid. That's how the oid is named, by two of the directions being that shape. Okay, and so technically the other direction is an ellipse, so it should be an elliptic hyperboloid, but all hyperboloids are elliptic, so that's okay. And if there are two variables negative, it doesn't matter which two, as long as there's two, so this is 1, negative. Oh, by the way, if this is 0 here, you'll get a cone. Because that waist in the center will get narrower and narrower and narrower until it comes to a point. So, but if there's 2 negative, then it's a hyperboloid of 2 sheets. Which is what you get when you take a hyperbola and rotate it the other way. And this plane in the gap there, that's the YZ plane in this one. I've drawn it up the wrong way. So the one that I have drawn is actually this one. That's the one I've drawn. Okay, so the actual surface itself goes upwards forever, like that. And there's this whole plane that you can slice down the center of it. There's a big gap on that plane, and that plane is the XY plane. And so the negatives tell you where the hole is, where the gap is. And then if they're both, if it's equal to 0, that's a cone, but it's 2 cones really, but it's what they call a double cone. And it goes on forever. And this axis here is the axis where the negative is. And it does go on forever up and down. And you see these 3 are in the same family because if you just change the constant term, you can switch one of them into another. So if I switch this to a -1 and then multiply everything by -1, it will give me this. So what will happen is if you start with this formula and you just vary this constant, with this constant positive, it'll be a hyperbola of 1 sheet. It'll just get narrower the smaller that number gets. And then when it gets to 0, the waist will become 0, it'll be a cone. And then when it goes past 0, the cone will separate and you'll get a hyperbola of 2 sheets. So with the ellipsoid, as you change that number, it turned into a point and then it vanished entirely. With the hyperboloid, it gets smaller and smaller, it becomes a cone, and then it turns into the other hyperboloid. I think that's all the ones that are really important. I know there are others, but pretty sure that's all the ones that are really important for Maths 1B. There is a list of like 20 of them, so I'm just going to talk about those. Oh no, there is one more that's really, just a second. The paraboloids. So the other ones are, so they're all the ones that have all 3 of them squared, except the one where everything is negative, but that's covered by the ellipsoid. So this is one where all the variables are there and all the variables are squared, and if you want to go into ones where all the variables are there but they're not all squared, then what you get is a hyperboloid, paraboloid. So you've got x squared on a squared plus y squared on b squared equals z, something like that. It could be z plus or minus c as well, it doesn't matter what's there, there could be a constant there. And this is a elliptic paraboloid. So the oid part is because if I cover up the x, I get a parabola, z equals y squared. If I cover up the y, I get a parabola. So since there's two parabolas, it's an oid, paraboloid, and then the other direction is an ellipse. If I pick a value for z, I get an ellipse, and so therefore it's the elliptic paraboloid. And the elliptic paraboloid is just a parabola that's been rotated. But again, this direction here is the one that's different. It's where the z is. And then there's also the hyperbolic paraboloid. Which looks like a Pringle. So the other thing made of string in the Maths Learning Centre is the hyperbolic paraboloid. Okay, so the one in the Maths Learning Centre is a bit pointier than that one. This is what we get if we slice it up and down with a circle cookie cutter. But if you slice it with a square, it would look a bit pointier. And it has this awesome saddle point in the middle. But it's Pringle shaped. That's the shape of a Pringle, which is a hyperbolic paraboloid. You'll find that most of those shade sails that they put up in public playgrounds are hyperbolic paraboloid-ish shaped because they have a saddle point. Yes. And I know it's hyperbolic because that is the hyperbola family of conics. And it's a paraboloid because that's a parabola and that's a parabola. So if I cover them up. So they're the main ones. Hyperbolic paraboloid is my favourite. Well, the two ones with, that are in the Maths Learning Centre are my favourite because you can make them out of straight lines. So all the other ones, you don't have any straight lines on them except the cone, which doesn't count because it's a cone. And then there's all these things. It can split into two planes. It can split into two planes that meet each other, two parallel planes. It can be a cone, like it can be a cylinder. So if you're missing an entire variable, it'll be a cylinder of some sort because the z can be whatever you want, so you can shift it up and down. So there's all these really cool things that you can get. And if you have a look at the other handout, you'll be able to see it. And that's the shapes of them. And so once you know what they're supposed to look like, and they never get you to sketch a 3D one, that's, oh gosh. Once you've figured out the shape of it, once you know that these will tell you certain shapes, okay, so this A, B and C here, the same as there's a box for the conics, there's a 3D box for the quadrics, and certain things will happen near the edges of that box. So those numbers describe how big the conic or quadric is. Once we're familiar with how all this works, we can go, cool, we don't have to plot points. We can just know for certain that knowing that formula, we can draw a box and figure out where our object is. The key issue is to get to this point. How do we get from a general conic / quadric to this? And that's the hard bit. But having a general talk about what they generally look like is good so that when they ask you, is it what type of quadric is this, you can answer the question. And it seems like a lot of work for like 1 mark, but you feel better, if you just know how to do that and you don't worry about it anymore. And at least you go, I can get that 1 mark, and it could make the difference between passing and failing. So there you go. And plus I love conics. So how do we get it into standard form? So there are several steps to this, and they involve moving the coordinate axes beneath the conic itself. So it's almost as if we have the conic exactly where it is, and we move the coordinate axes around underneath it. Okay, so the conic stays where it is, and instead of conic stays where it is, and I move the coordinate axes around underneath it until it's in a format that I can say, well, relative to those axes, I can draw it, and then I can work backwards to figure out the one I was actually looking for. Now, I don't want to risk making up an example that's going to be really awful, but I may have to. So, these are the steps. First, we want to write it with matrices. Write it as a matrix equation. And then the matrix that comes out of that equation, we're going to have to orthogonally diagonalize it. Okay, so we're going to have to, in step 2, there's all these sub bits, we're going to have to go orthogonally diagonalize the matrix A, which will require us to find the eigenvector, find the eigenvalues, find the eigenvectors. We may possibly have to do the Gram-Schmidt process within each eigenspace. Do the Gram-Schmidt, and then P is the eigenvectors as columns, and D is eigenvalues along the diagonal. All right, so that's the biggest step of this. And you'll often find that that step will be in a different question in your exam. It'll be question 3, and then you'll use that in question 4 or something. Okay? And you'll often find that they'll do part of the work for you. Okay? They'll tell you what the eigenvalues are, and you'll just have to find the eigenvectors. Or they'll tell you 2 of the eigenvectors, and you only have to find the 3rd one. Okay? So they'll often in an exam do part of the work for you for that. Okay? And it may not be necessary to do this at all. I will tell you why we're doing this in a second. Okay, and then you're going to go sub in x equals p, and they normally put a dash on that. The dash apostrophe there really confuses me, because over in dynamics, when you do x dash, you mean the derivative of x, and so I tend to call it xr for rotated x. Okay, because what this whole thing is to do is to rotate the coordinate axes underneath your conic or quadric. And so you'll also get that x transpose will be xr transpose p transpose. Okay, so you sub both of them in. So you take your original equation and you replace the x's with those things, and then what you get is a new matrix equation. And then step 4 is to now rewrite that matrix equation as an ordinary equation, okay? Okay, so the whole purpose of this part of the working is to make the x times y's and the y times z's go away. Okay, so the whole point of this is, just let me rotate this for a minute. This is to remove what they call cross terms. So, if your equation already doesn't have any cross terms, if it doesn't have an xy or a yz or a zy, you do not have to do this part of the working, and you can skip straight to part 5. Really important. Okay, so if it doesn't have any cross terms, this part of the working isn't necessary. So step 5 is now to complete the square for each variable separately, but only the ones that are squared. Complete the squares. And then from after that, you should be able to have enough information. It should be in standard form now, but the final step, and so to complete the squares, what this does is it removes the linear terms and leaves only the squared ones. So remove the linear bit. And then part 6 is to arrange for all your coefficients to be on the bottom and for your 1 to be over there. So divide to get a 1 and arrange the coefficients to be on the denominator. And then it will be in properly standard form. Okay, once you've got it once you've completed this, once you've written it as an ordinary equation, there's only a few options for what the quadric or conic could be at that stage. And if you don't have time to finish the completing the squares, you can say, well, at this stage I can tell it's either an ellipse or a point or empty, something like that. Okay, so the completing the squares, what this will do is it will tell you what the constant is at the end. So I'll do an example so that you can see how that's done. But that's the process. If you can remember that there's two main steps, there's the removing the cross terms, which is a bit that requires the matrices, and there's the completing the squares, and there's three main steps. If you can remember that there's three main steps, it will help you to focus when you're doing it, and also remember what each step is for, so that you can notice if they've done part of it for you. Okay. All right. Has someone got their notes, and I could possibly do an example or a tute or something? You know what? I've got my uni open. Maths 1B.
Question 4 of the 2013.
Okay.
There's one there.
That would be under exam info then. That would be under Algebra 2013, semester 1 or 2? That one? Okay, cool. So my example will be this example. So this example is 2013 semester 2 algebra exam. Question 4. Okay. Alright, it says write the quadratic form in the form x transpose ax in which that is that. Okay. So I'm just going to use the example there and just run with it and not necessarily do the actual exam question. Just so that you can see how you would do the whole thing. So it's 2x squared plus 2 root 2xy plus y squared. Okay, and they haven't given me a constant term. Okay, so this one's not going to require us to complete the square in this exam question. So you'll notice they'll often only give you half of it. But so that you can see how it, it doesn't matter. I'll do the other one as well. I really would like you to see how this works. So I'm going to add, is this a bad plan? Yeah, it's a bad plan. I'm just going to do the one that's in the notes. Okay, so the actual question that's in the exam has an equals to 12 in it later on. So that's my conic. Yes, it's a conic because I'm in 2 dimensions because there's only an x and a y. If that was a 3D quadric, it would be a cylinder of some sort, but it's in 2D. So the first step was to write it as a matrix equation. Okay, so the bit involving the x and the y, the squareds and the xy, that will become a matrix. And so what we're going to do is we're going to, there's going to be x, y here and x, y here. So this one on this side is a row because you can only put rows on the left hand side. This one's here's a column. And you can imagine having headings for this. We've got x, y here and x, y there. Okay? And so x and x, that would give me x squared. So that would be a 2. There's 2 lots of x squared. And y with y, that would give me a y squared. There's only one of those, so I put that there. And this is x. So this is y and x, and this is x and y. So they're both x, y, and together they are 2 root 2. So I spread that 2 root 2 evenly across these two things here. So I divide that by 2 and put them in those spots there. technically it would still actually be correct if I just put 0 in one of them and 2 root 2 in the other. I can spread them across those two in whichever way I like, technically. But if I want to do orthogonal diagonalization, I have to arrange for them to be the same, or it won't be able to do that part of the working. So that's what I've got. And so this is our X as a row, so X transpose. This is my matrix A. This is my X as a column, and the 12 is still 12. Okay? So stage 2 would be to orthogonally diagonalize the matrix, right? So part A, you don't have to call them 1, 2 and A and whatever, you can do whatever you want. I need to find the eigenvalues. Now they've told me in the exam that they happen to be 0 and 3, I think. Yep. Alright. But one way of checking that with a 2 by 2 is that the determinant of that matrix comes out to 0. So 0 must be one of the eigenvalues, and the eigenvalues have to add up to the same as the trace, and so the other eigenvalue has to be 3. So, but exam did this for me. And so I've got lambda equals 0 and 3. And the next stage is to find the eigenvectors. So if lambda equals 0, then lambda I minus A is 0I minus A. And if I shift the bottom one up to the top and times it by minus 1, and if I times it by root 2, I will manage to make it the same as the other row, and so I'll be able to get this. And in Maths 1B, it's okay to not show all your row operations. Okay? You know that it must have a free variable. Okay? With eigenvalues, it must have a free variable, so you can shortcut your working with a 2 by 2 and go, well, therefore the two rows must be combinations, and I'm going to get a row of zeros. So you just pick one of the rows and make it into a 1 in the appropriate spot, and then make the other one 0. That's actually a perfectly acceptable way of going about things. Okay? Okay, so what I've done is I put my pivot here instead of here because I didn't want to divide by root 2. So my free variable is that. So that free variable will be t, y will be minus root t. So my xy is my root 2t. So my xy is t lots of 1 minus root 2. So that's my eigenvalue for 0, eigenvector for 0. Okay? And since they specifically asked me for the eigenspace, normally you would say, the eigenspace for 0 is the span of 1 minus, like that. Okay? If they didn't ask me for the eigenspace, I'd just leave it like that. They're my eigenvectors. So part B, the other eigenvalue is 3, and lambda I minus A would be 3 I minus A. So 3 minus 2 is 1, leave the minus root 2, minus root 2, 3 minus 1 is 2. By the same token, this must be a multiple of that because there has to be a free variable. With 3 by 3, it's not so straightforward, so you have to actually do the row operations. It should be able, the row operation will be row 2 is row 2 plus root 2 of row 1, and I'll get this. So with my row operations, so that's my pivot, and so I've got that that y is t, x is root 2t, and so therefore xy is root 2, 1. Which is good. It should actually look like more often than not it looks like the other eigenvector, but with the numbers in the opposite spots. So that's just a good instinct thing to know if you go on the right track. So they're my eigenvectors. Okay, and the next stage was to possibly Gram-Schmidt each eigenspace in order to produce an orthonormal basis for each eigenspace. I don't have to use the Gram-Schmidt process because there's only one vector in each eigenspace's basis. If there were two, I'd have to do Gram-Schmidt just within them, but as it is, I can just divide them by their lengths. So this would be, I can also say to normalize my basis, right? So normalize my vectors. So the length of root 2, 1 is root 3. So I'm going to have to divide by root 3. Really hoping I'm doing this right because there's a lot of roots there and it doesn't feel good. So choose my basis for eigenspace. So choose root 2 on root 3, 1 on root 3. That's crap. 1 on root 3, root 2, 1. For lambda equals 3, and 1 on root 3, 1 minus root 2, wasn't it? For lambda equals 0. Let me check if I've got my original vector right. Yep, and they'll be the same length because they've got the same numbers in them. Okay, so I've done that, and then my matrix P, so finally P equals those two as columns, and so but you're supposed to arrange them so that the determinant's positive. So let's just try this round. If we had it round this way, root 2, 1, 1 minus root 2, we'll get 2 times, no, that's going to be negative. We want them round the other way. I'll keep putting a stroke there. And everything's multiplied by 1 on root 3. So that's my matrix P. And the determinant of that matrix is not 1. Let me just think this through. Root 2 squared is 2. 1 squared is 1. It's definitely root 3. It's definitely root 3 long. Oh, I hate this. Oh, that's okay, because when you find the determinant of something, you have to multiply by that number twice. Okay, once for each row. Awesome. Okay, so because the whole matrix times by root 1 on root 3, the determinant gets multiplied by 1 on root 3 twice, once for each row. Yay, okay, so the determinant is 1, so that should be working. That's just a check that I've done it right. And so that's my matrix P, and my diagonal matrix will necessarily have the matching eigenvalues along the eigenvector. So the 1 and minus root 2 match with 0, so that goes here, and the root 2, 1 matches with 3, so that goes here, and all the other entries are 0. So that's what I get for my diagonal matrix. Okay, so we're specifically focusing on those two being the eigenvalues. And they have to match with the eigenvectors that you put in. So if I switch these two, I would have to switch those two. Okay, cool. So I've done part 2. And then part 3 says I need to sub in x equals pxr and x transpose equals xr p transpose. And so I'll go back to my original matrix equation that I had, which was x transpose a x equals 12. That's what I had. And this says that I need to replace the x with pxr and the x transpose with xr transpose pt. So this is replaced with xr transpose pt. This x is replaced with pxr, like that. And I know that P transpose AP is actually D, because that's the whole point of this process. Okay? So XR transpose dxr equals 12. So that's telling me that my rotated x and my rotated y as a row, my matrix D, and my rotated x and my rotated y as a column comes out to 12. Alright, so my final step is to write this as an ordinary matrix. So write as an ordinary equation. And so I'll do the same process that I did for the other one, but backwards. This one will have to be the coefficient of xr squared. Whoops, sorry. 0xr squared. This one will have to be the coefficient of yr squared. And these two together are the coefficient of xr, yr. Now it's not necessary to do all that stuff that I just did, but the entire point of this is that once you've done this diagonalization process, both of those will be guaranteed to be 0, and so you won't get a cross term. That's the entire point. So in our particular case, we get 3yr squared equals 12, which is telling me that yr squared is in fact 4. All right. So the next stage would be to complete the squares, but I don't have to do that because I don't have any linear terms. The whole point of that is to get rid of linear terms. And then I should divide to get a 1 and arrange for the coefficient to be in the denominators. Well, that's if I had an ellipse or a hyperbola. This is 2 lines. Because I've only got 1 square family, and in the 1 square family I had the parabola and the 1 line, 2 line empty situation. So this is in a parabola family because it's only got 1 square. And in my parabola family, I should rearrange it to get y, x equals y squared. But there isn't an x, so I'm just going to have to leave it like this. So what I can actually do is my last point, don't have to complete square necessary. And my stage 6 is to get my standard form. Well, it's already in standard form for the shape it's in. Okay, so I've got yr squared is 4. If I solve that, I get yr equals plus or minus 2, which is yr equals plus 2 and yr equals minus 2. It's 2 parallel lines. Okay? That was sneaky of them, right? I reckon the lecturer who wrote this, actually, I remember being really upset at this lecturer last semester because of this exam question. I had people coming out of the exam and coming into the Maths Learning Centre and going, David, that was awful. Because yeah, I remember now. So they were actually trying to be really friendly because there's all these lovely zeros and it comes out to a simple equation. But it's not one of the ones that was on the list that you were really told in lectures. It didn't tell you the 2 parallel line thing. Well, now you know. That's 2 parallel lines. They're actually y equals 2 and y equals minus 2. But now let's see, if we're going to sketch this, I know that that's not necessary, but we can sketch it. And I'm going to show you something important about how sketching works. I know it's going to be on an xy axis, so I'm going to draw that first. X and y, okay? If I go back through my working, I will be able to find the information I need to draw the graph. So if I go back through my working, my matrix P will tell me where the xr and the yr axis point. So if I go back to my matrix P, see this vector here? That points in the direction of the the xr axis. And this vector here, it points in the direction of the yr axis. So these are my rotated axes. So I'm going to add them to my graph. So if this is 1 here, then root 2 is about 1.5. So I've got the vector 1 minus root 2, so 1 minus root 2, which is about there. That's the point 1 minus root 2. And if I had a ruler, I'd be doing a really good job. And my x dashed axis has to go there. through the origin actually, but you know, we're close. So that's my rotated x-axis. And if we just do the other column of P, the other column of P is root 2, 1. So root 2 is about there. I go up by 1 and there it is. And if you've done everything correctly, these will be at right angles to each other, as they should be if they're coordinate axes. Okay. So my matrix P told me how to get those coordinate axes. I don't have to figure out angles to figure out how far it's been rotated. I can, but I don't need to, because I can just use the vectors that are there to directly draw this. The next thing is, I'm going to turn my page so I have the XR and YR axis the right way round. Okay, so now I'm going to draw my conic relative to that. And I was told that my conic eventually was YR equals plus 2 and YR equals minus 2. So, if that's 1 there, if I draw a circle, that'll be 1 there, there, and that looks about like 2, about there. Can't be sure, but it looks about right. So, probably 3. But that's okay. I just need to mark roughly where 2 is. So this is 2 on the YR axis and minus 2 on the YR axis. And then y equals plus 2 is this. And y equals minus 2 is this. And then, if I turn my page, magically it's where it's supposed to be. So that's my conic. So conic is drawn in purple, just for the reader to know where it is. Okay, so that, oh look, I've got this lovely visual illusion. It looks like it's going outwards because of where all the lines are. Okay. So that's not your standard conic, right? It's not the normal thing that would happen in an exam. And I should do another example that has the completing the square as well, and that will, where the sketch will come out different. I could do a 3D one, but I feel like that might be going too far, and I can't sketch that. So I don't think they expect you to sketch them anymore. Did they ask to sketch in that one? No, they did. Hence determine the nature of the curve and provide a rough sketch. Awesome. There you go. And you see, the lecturer thought they were being really nice because they went, oh, it's really easy to sketch 2 parallel lines. But because he didn't show specifically parallel lines, yes, I was very upset at him. Okay. So, I should do one that's got the other stuff in it. Sorry? Don't know. So I could probably skip that and do the other one. But the completing the square, I just want to do just one little bit on completing the square, not necessarily do the whole thing. Okay? Just the completing the square bit. Okay, so what if we had the same one? No, I'll just do completing the square. I mean, I prefer to do a really good job so that there's a whole thing on it rather than cover the other stuff, because I can always move to another lecture theatre and keep talking about the other things. So completing the square, managing completing the square can be quite difficult And so you'll often get to this stage. So suppose we got to here, right? No idea what this number is, whether it's going to be useful, but let's run with that. Okay, so the first thing is that before you complete the square, just looking at this bit, I can tell it's going to be a hyperbola or two lines. They're the only options for what it could be. Because when I complete the square, it will still have a 2 times something squared here, and it will still have a minus 3 times something squared here. And so once the square is completed, it will be x squared minus y squared equals something. And it all depends what that something is. If that something comes out to be not 0, then it will be a hyperbola. If the something comes out to be 0, it will be 2 lines. So at this stage, I can say could be hyperbola or 2 lines. Okay? So it's just good to know that. And that's why it's good to know the families. If they were both positive, you can say, well, it could be an ellipse, or it could be a point, or it could be nothing. And if there was only one square, you would know it would have to be a parabola, unless, of course, one of the variables was missing. And in case you would be parallel lines. Okay, so it's just good to know that that's probably going to happen. And we're going to complete the square. And so what we need to do is we need to combine our x's and y's in with the x squareds and y squareds. And so the first stage, to make it easier, would be to bring this over here to be near the x's so I can see what's going on a little better. Okay, easier to see. Right. Well, the first step after that is to take out the constant that's in front of each of these things. Okay, even if it's just a minus, you have to take the minus out. So if it was just not minus 3, but just minus, in fact, why don't I just do it that way? If it's just a minus, you still have to take it out. And don't forget to bring the minus with you. So that 2 has to come out, and so I'll get 2x squared minus 5 root 2x. Oh, that was a bad plan of mine, but that's okay. And I have to subtract, I would have to take the minus out of both of those. Okay. And so the plus 6y will have to become a minus 6y because I took the minus out. And the way that completing the square works is that the next stage is to write, leave a gap so that there's room to do your working. I need about 3 lines, so okay. This is what I'm aiming for. So this is supposed to turn into this, and so it's got an x there, and because that's a minus, this will be a minus, and this will be y minus as well. Sometimes it comes out to be y plus. If this was a plus here, this would have been a minus here. Plus here, they'd both be the same. If that's a plus, then that would be a plus. Okay, so the 5 root 2, that number that's next to the x will have to be divided by 2, and so I'll get 5 on 2 root 2, that's my number. And then I'm going to, working backwards, expand this out. So if I expand this out, going upwards, it'll be x squared minus 5 root 2x plus the square of, on 2, sorry, you know, that's right, times 2. So it'll be this squared plus this squared minus this times 2. Okay? And so I'll have a plus 25 on 4 times 2. So I'll have the square of this here. That's what I would get if I expanded it out. But I don't have a 25 on 4 times 2 here. So I'm going to have to, in this bracket here, add it in and subtract it. Okay, I didn't leave quite enough space to do that. And that means that if I expand this out, this bit here is still here. And so when I expand out this 2, the 2 times all of that is still there, and the 2 times this is minus 25. So with the y's, I'm going to do the same trick. This has to be 3 because 6 divided by 2 is 3. If I expand this out, I'll get y squared minus 6y plus 9. But I can't just go willy-nilly adding a y squared, adding a plus 9. So I will have to, up here, go plus 9 minus 9. And then if I expand this out, I'll get minus all of that, which is still here, and minus minus 9 is plus 9, and the 8 won't change at all. And so I've got minus 25 plus 9. And so now I can rearrange all my numbers to get what I'm looking for. You know, put all the numbers over there with the 8. So it looks like it's a hyperbola then, because my number over there is not 0. So 8 plus 9 would be 17, plus another 25 would be 37 plus 5, which is 42. So that's my completing the square step. The next, at this stage I can tell it's a hyperbola. So if all they want is what is it, you can stop there. But if they want it in standard form, you have to arrange there to be a 1 here. By dividing by 42. That's getting the 1, and then I arrange for these to be squares. And now it's fully in standard form. So what this is telling me is that the centre of this hyperbola is at 512 root 2 and 3. That's what those two numbers there are. That's the centre of the hyperbola. The radius in the x direction is this, the root 21. The radius in the y direction is root 42. And it's going to point along the y-axis. The hole is going to be on the y-axis. So that's my ordinary axis. My translated axes are at 4, 5 on root 2, hey? 2.5 lots of root 2. Root 2 is about 1.5. It's about 4 and a bit. So sort of here, about there is the centre. And so that's my translated x and y axes. And then my box will be at root 21 and root 42, whatever the hell they are, which is sort of 4-ish, right? So that's my a and my minus a. 40, yep.
Shouldn't it be 24 instead of 42?
Oh, probably. Oh, it's 8 minus 9. Awesome, thank you. I added the 9 instead of taking it. Thank you very much. Thank you. Yes, 8 minus 9 is minus 1. Yay. Okay, so that means it's actually here. So that's close enough. Root 24 is nearly 5. And so there's my box. And my hyperbola would have asymptotes in through the corners of the box. And the hole is on the y-axis because that's where the minus is, and so it's actually here. So, there we go. Right, so that's the last stage after you get to completing the square, to try and figure out what it is. If you had to rotate before you got to that bit, then you would have had to draw your rotated axes and then turn your page and then draw your translated axes and draw it onto that. And so I don't think they expect you to do that in exams anymore, but I can't be 100% sure. Okay. There it is. All right. So that's probably quite enough of doing conics right now, unless you have any last questions before I move away from there. Cool. There is another one, I think I'd talk about it. Be careful with what happens with the constant bits, with the linear part, when you actually put the matrix in. And I'm just going to have to leave that for now, but do be careful, and if you want to talk about that, feel free, but they often don't get you to do both at once. Okay, so I won't talk about proofs. I will talk about those in proper intervals, though. So what were your particular questions, though? Yeah, not sure? Yeah, making sure that people didn't kick us out. Yeah. Just actually, therefore, I will do this then. Just be careful at the point where you put the P in. So at that step 2, step 3 of subbing in, let's just do an example. So suppose we were at this stage. I need to actually say what the A is, sorry. Oh, it should be symmetric, shouldn't it? Okay, so suppose we had that. Oh, crap. Give me some, I'm just going to start again, sorry. I have to know what the matrix is. Okay, so I have to design it to have the eigen things I want. Okay, much better. So suppose we had X transpose 1 0 0 0 0 2 1 1 2 X plus so remember that your original matrix, your original equation, you'll get, like that would have had a 1x and a 3y and no z's. Okay, suppose this is what we had, and we were trying to sub in this they're all root 2's, by the way. So trying to sub in that. So when you do that, you know that they traditionally call this A and this K, right? So you've got X transpose AX plus KX equals 7. Okay, and so what you'll do is you'll sub in X transpose is P transpose XR transpose, and XR is PX. No, sorry, X is PXR. You'll sub in that. So if I'm subbing in that, then I'll get XR transpose P transpose A P XR plus K, and the X is replaced with PXR, right? So don't forget to put the P in when you do this. That's a really key step. So we know that the P transpose AP will have to be the eigenvalues. I will just pop them in if you don't mind. They are 1 and 3 and minus this plus 1, minus 1. No. And another 1. Okay. Yep, okay, 1 and 3 and another 1. And so I know that this is D here, but I don't know what the KP is. I'm going to have to figure that out separately. So KP is 130 times 100, 0, 1 on root 2, 1 on root 2, 0, minus 1 on root 2, 1 on root 2. So I've got this times that is 1. This times that is 3 on root 2. And this times that is minus 3 on root 2. And so therefore I've got XR, YR times my D, ZR, plus this new KP times XYZ, and the 7 is still equal to 7. So just be really careful when you sub it in that you don't forget to do the KP part, so that you don't get it wrong. And then when you expand this out, you're going to get XR squared plus 3YR squared plus 1ZR squared plus XR plus 3 on root 2YR minus 3 on root 2 ZR equals 7. And you'll have to complete 3 squares. Not that I'll do that bit, but that's what you would have to do. But we can tell at this stage if it's going to be anything at all, because all 3 of these are positive, it's going to be either an ellipsoid or a single point or empty. So we can tell at this stage what it is. So we don't have to complete the square, and we can still get that, at least maybe half of that mark, if it made a difference between like a distinction and a high distinction, or a pass or a fail or something. So can tell it's an ellipsoid or a point or empty, depending on what happens after we complete the squares. Though most likely to be an ellipsoid, it would have to be really, really specific for it to come out to one of the other two. Well, it's really unlikely for it to be a point, but it could be empty. Can't be sure. So that covers all the different pieces of that. I didn't give you one long example that had all of those bits in it, though to be fair, in an exam they usually don't expect you to do all pieces of it. They'll do part of it for you. So, cool. Much better. Okay. So, thanks very much. I'll stop there unless there's any more questions about conics and quadrics. Cool.